All right, let's take a look at our little practice quiz in preparation for tomorrow's real quiz. Going to look remarkably similar to the fake quiz that you see up on the board here right now. This one says a swimmer heads directly north across a 200-meter wide river at 4 meters per second, but there's a current, a river current, that's 2.00 meters per second to the west in the river. So let's draw this vector diagram out, remembering, of course, that when we can't include both velocity and displacement in the same vector diagram. It has to either be displacement or velocity. And since we're trying to find a velocity, and since we know more about velocities than we do displacements, let's make our vector diagram one that has velocities instead of displacements. We're going to make this 4 meters per second a solid line vector. Remember, solid line vectors are vectors that contribute to my actual motion, not the actual motion itself. I don't go directly north across this river, but I head directly north across this river, or I aim directly north. This is a solid line vector. This is contributing to whatever my actual motion is. Now, we also have a river current that's flowing to the west. That's also going to be a solid line vector, drawn about half the length of the 4 meters per second solid line vector. This river current also contributes to my actual motion. I'm not going 2 meters per second to the west, but that 2 meters per second to the west contributes to where I actually go, or to my actual motion. My actual motion is my motion relative to the shore, which is my dotted line vector right here. So if I aim directly north, but then there's a river current that's to the west, where do I end up going? Somewhere north and somewhere west. Now, have I drawn this vector diagram correct? I've drawn everything in the right direction with solids and dotteds and so on, but should the solids be front to back or head to tail? Absolutely. What about this red dotted line? Is that drawn correctly? It's drawn from start to finish. Yeah, good. That's drawn correctly as well. We want to find the velocity relative to the shore, so we want to find the resultant vector, and we want to find the angle. It doesn't say find the angle or find the direction. How do you know on your quiz tomorrow when I say find the velocity of the swimmer? How do I know to find the angle? Good. Velocity is a vector. It requires direction. So even if it doesn't say that, you got to find the direction. The only time you wouldn't have to find the direction would be if it said what's the speed of the swimmer, the actual speed of the swimmer, as opposed to the actual velocity. All right, so we can find the value of r here now fairly easily. Okay, r is going to be equal to the square root of 2.0 squared plus 4 squared. What do we end up getting for that? Who's got that? Square root of square root of 4 plus 16, square root of 20 is 4.47. We're going to round that to, it would be 3 digits, wouldn't it? 4.47 meters per second. 3 digits because, of course, this is 3, and this is 3. Now, we want to find our angle as well. So we're going to say theta is equal to the inverse tan of opposite over adjacent. What's my opposite side here, 4 or 2? 4? Yeah, it's 2 actually. Yeah, it is 2. So the inverse tan of 2 over 4, that gives me an angle of what? Inverse tan of 0.5. So we got 27 degrees here. This would be west of north. And it's west of north because, let's look at this. In order to get to this spot, I have to go north, then west. Or, in other words, I have to go west after north, or west of north. Now, the other way to look at it is this angle right here that this dotted line is at is measured from which axis? Well, it's measured from the north. It's not measured from the west, because this is the west. Right? Nothing's measured from the west here. It's measured from the north, or it's measured of north, west of north. So 27 degrees west of north. Now, JC just pointed out, I think, that he drew his diagram like this. And when he did, he would have got an angle of, what, 63 degrees? Okay, his angle would be 63 degrees north of west. Would that be correct? Yeah, that's exactly the same thing, just a different way of expressing it. Good. Now, question B says, how long does it take the swimmer to cross the river? This is where I might want to draw in my river. The width of my river is 200 meters. I'm putting it in the diagram, but notice it doesn't actually form part of my vector diagram. And remember, the vector diagram has to be either velocity or displacement, but not both. For this one, we're going to use the equation V is equal to delta D over delta T. And we're going to rearrange it to solve for delta T. It becomes delta D over V. Now, what distance do I use here? What displacement do I use here? I only have one, right? So probably I'm going to use that one. I could find some other displacement using the angles, but it probably makes sense to use the 200 meters that I'm given here. Which velocity do I use? The 2, the 4, or the 4.47? Who says 2? Who says 4? Who says 4.47? You're right. I'm going to use the 4.0 meters per second. Can anybody explain why? Why not the 4.47? That's what some of you guys did yesterday. Good. Because the velocity and the displacement have to be in the same direction. Whenever you're using an equation, any equation, not just this one, but any equation with two vectors in it, those two vectors have to be in the same direction. Okay, you're going to learn an equation in our next unit, F is equal to m times A. A and F have to be in the same direction. Next year, in Physics 30, you're going to learn an equation, delta P is equal to F times delta T. Whatever delta P is, doesn't matter. You know right now that F and delta P must be in the same direction. So if I'm using V is equal to delta D over delta T, delta D and V must be in the same direction. If I'm using the displacement across the river, then I have to use the velocity across the river. I could use the 4.47, but if I did, I'd have to use that displacement, which I don't know right now. All right, so 200 divided by 4 would be 50.0 seconds. So the answer to question B would be 50 seconds. And then how far downstream do I go? Well, downstream is a displacement this way, right? If I want to find the displacement horizontal or the displacement downstream, then what velocity am I going to use? I got to be consistent, right? Blake? The horizontal velocity, 2.0 meters per second, times a time of 50 seconds. Now, we talked about this a little bit yesterday. I can't mix and match velocities and displacements. So the velocity for B is completely different than the velocity for C. So is the displacement. But the time is going to be the same. How come I can make time the same for X and Y, but I can't make velocity or displacement the same for X and Y? Yep. Because time is a scalar and velocity and displacement are vectors. Good. Good. So 2 times 50 gives me 100 meters. So I end up 100 meters downstream.